Right, hello everyone. So we are going to do tutorial on chapter 4, cooling load estimation table. So this is an example of question for cooling load problems. So based on the question, a space is to be used for general office. It is to be air conditioned for human comfort. Estimate the peak cooling load. Requirement based on the following construction details. So this is the characteristic. First is the room size, 65 multiplied with 65 feet. This is the area multiplied with 10 feet ceiling height. Okay, and then the wall, it is made by 4 half-inch brick plastered on both sides. And then on the north glass, we have 4 number of glass multiply with 6.5 multiply with 5 feet. Okay, it is made from a single regular plate, 0.25 inch, no shades. Okay, no shades mean bare glass, with internal blind of medium color. Okay, and then east glass, west glass. For the door, we have 2 door. It is also made by glass. Okay, each on east and also north direction, and the size for each of the door is 5 feet multiplied with 7 feet. And then for the roof, we have a corrugated asbestos with suspended ceiling board. And then for lighting, it is made from it produces 4 watt per square feet. Okay, fluorescent type. And then for equipment, we have 40 number of office equipment, and each of the equipment is rated at 350 watts. And then occupancy is suitable only for 50% fixed. And then sorry, this is maximum. Okay, so our design is based on this 50%. And then room condition. Okay, so room condition, we want to condition the air to be 75 Fahrenheit temperature, 55% relative humidity, and also 72 grain per pound relative humidity. Sorry, specific humidity. And then for the outdoor air, 92 Fahrenheit and 136 grain per pound. And our air change is designed to be 1 air change per hour. So let me start to understand this problem, and then we go for the cooling load estimation table. So before we want to fill this cooling load estimation table, students must know the table. Okay, air conditioning load estimation table. So this table consists from table 1 until table 12. Table 12, and all of this table is very table 13 is very important in order to estimate the total cooling load for sensible and also latent heat. Okay, so for example, table 1, they have a occupancy, fresh air, grand total, etc. So let's go to the problem. Okay, here, so look at the question and also table. Right, so first we need to fill this space used for. Okay, so just now the question asks for general office, so I have highlighted here, right here, office, general office. Okay, the equipment operation for office normally is set to be 12 hours per day, and then the size is estimated to be 65 65 multiply with 65 feet. Okay, 65 multiply with 65, so it equal to 4,225 square feet. And then the height of the buildings is 10 feet, so we multiply again with 10, it becomes 4,250 cubic feet. Right, that is the volume of the air inside that buildings. And then we need to fill up the psychrometric analysis for the outside air room and also the difference. Okay, so from the problem, the outside air is 92 Fahrenheit and also the relative humidity is 136 grain per pound. So I write here 92 Fahrenheit, that is your temperature. Okay, and then for room temperature is 75 Fahrenheit, and then the specific humidity outside is 136 grain per pound. We want to reduce into 72, right? Okay, we want to reduce into 72 grain per pound. So the difference of temperature is 17, and the difference of specific humidity is 64. Okay, so this is the only important, temperature and also specific humidity. So the relative humidity basically is not so important. Okay, so the important only specific humidity. Now we go for the ventilation. So this office is equipped with 50 people, multiply with CFM per person. So to get the CFM per person, we need to refer into our table. Okay, alright, so to get the value of CFM per person, we need to refer to clean load estimation table, table 11, which is a ventilation standards. So our problem is general office. Okay, here. So the value for CFM per person, we have two types, which is recommended and minimum. Normally we take recommended value, which is 15 CFM per person, and then we write into our table 15. So 50 multiply with 15, it becomes 750 CFM. On the second row, second row is ventilation by the area. Okay, so the area of this office is 4,225 square feet, multiply with CFM per square feet. So this one we need to refer table 1. Okay, so table 1, here. Okay, CFM per square feet for general office. Right, so based on table 1, we need to find office buildings. Okay, office building is a place which is very big. Okay, so for our problem, general office, which the dimension is 65 feet to 65 feet, it's suitable to use a private office. Okay, private office. So our CFM per square feet is here. We take the average value, which is 0.15 CFM per square feet. Okay, so I write here 0.15. So the value 0.15 multiply with 42225, you get around 634 CFM. And then for the third row is the ventilation by air change, we set to be 1 exchange per hour, and then the volume is 4225 divided by 60. Okay, so you get the value of 4225 70.4. So our preferred CFM is the maximum between these three rows, so it should be 750 CFM. Right, next part is we want to fill up the solar heat gain and also transmission heat gain for this office. So before we do that, we need to construct a simple table just to calculate the area of our problem. So based on the question here, north, east, west, and also there is no mention or details about south direction. Okay, first we need to construct a simple table here. Okay, area, we need name is area table, because the building is made by glass and also wall. So I write here glass and also wall, and I need to know what is the area for this type of material. So here is the direction: area north, east, west, and also south. Okay, glass, the area in the north direction. Okay, 4 multiplied with 6.5 multiplied with 5. So 4, 6.5 times 5, and then we need to add another type of door. Okay, because it is also made of glass, which is 2 door on east and also north direction. So east you have 2 door, north also you have 2 door. So 2 multiplied with 5 multiplied with 7. 2 multiplied with 5 multiplied with 7. So you get the area to be 200 square feet. Okay, and then for east direction, okay, for east direction, so you need to know from the details from the question, 4 times 3.25 times 2.5. 4 3.25 multiply with 2.5 plus, okay, plus so same 2 5 7. Okay, you got 1. Okay, you got 1 to 0.5 square feet. West, so for west direction, 4 6.5 multiply with 5. Sorry, 4 6.5, sorry, multiply with 5, we get 130 square feet. And for south direction, there's no detail that this direction have glass, so it should be 0, right? And then for wall direction, so basically we need to find the total area for that direction minus the glass direction. Okay, for example, we know that the height of the building is height of the building is 65. The areas is 10 feet. right? Means that on the north direction, the area in that direction is 65 multiply with 10. Okay, this is the total area, 65 multiply with 10, and then you need to minus with 200. So 200 come from the glass area, so you got value of 450 square feet. Okay, and then you do for the rest. This one should be 547.5 square feet. This one should be 520 square feet, and the last one 65 times 10. Okay, right, so this is the area table. Now we have already know the area for each of glass and also wall. We need to fill up into our cooling load estimation table. So first on the nodes area, so the area here should be nodes glass 200. Okay, so 200, this one should be 200. Okay, however, for solar heat gain, what is meant by solar heat gain is that the direction that directly exposed to the sun, and we know that the sun is rise from east and the sunset at the west. So only these two direction is counted. So for the north and also south direction is not counted. So I put empty here, right? Dash. This one also dash. So each time you calculate the solar heat gain, no need to consider north and south direction. And then so for the area for east direction, for glass is 102.5. Okay, and for wall is 547.5. So this one is wall, so I should fill 547.5. For west direction 650. Sorry, for west direction again we check. It should be 520, right? 520 square feet. So here 520. Okay, and then this is BTU, British Thermal Unit. Alright, it stands for the temperature difference for solar heat gain. So we need to refer table 7. Okay, so look at table 7. Table 7 on the east and also west direction. So this wall is made by brick wall. Okay, so for brick wall east and west direction, the value is 16 and also 30 pound per square feet. So we fill here 16 and also 30 east and also west. And the last part for solar heat gain on east direction is thermal coefficient. Okay, heat thermal coefficient you from table 9. So check again table 9. Okay, transmission coefficient for common building structures. Okay, so in this table we need to find on the wall, right? The wall we have two types, external and also internal. External wall is the wall that directly exposed to the sun, while internal wall inside the building. So we should get external wall. So for our case, it is made by 4 half brick wall with cement plaster on both sides. So the value of U is 0.48. Okay, so now we fill up again 0.48 here, then 0.48 here, okay, because it is same. And then you calculate the total BTU per hour. 547.5 multiply with 16 multiply with 0.48, you got 4205 BTU per hour. Another one is 7488 BTU per hour. Then for the next part is for glass. Okay, for glass we need to consider also east and also west, because it is directly exposed to the sun. Right, the area for east for glass is east is 102.5, and then for west is 130. Okay, 102.5, and sorry, this is not. East is 102.5. For west is 130, and then multiply with the temperature difference from table 4. So switching table 4. Okay, so we need to find the east and also west direction. So many people ask which months we need to use. So based on this east and also west, we need to take the highest value of exposure, because we design the air conditioning at a maximum point. So if we design 147, when we reach September, the value will be higher than the requirement, and then our cooling load cannot sustain the value of this exposure. So we need to take the maximum value, and the maximum value always occur on the September each of the year. So both east and also west is 167. So fill up the table 167, 167, and then multiply with table 5. Table 5. Okay, east and also west. Okay, mark here. Right, so which weight of the buildings we need to use? So we know that the wall is made by brick wall, brick wall. So in this brick wall, right, to check the weight of the brick wall, we can refer here. For half brick wall with 5/8 inch plaster is about 60 pound per square feet. So we back into table 5. Okay, so the storage load factor is based on 60 pound per square feet, but the value here only have 30, 100 and 150. So we need to take higher than 60 if there is no 60 pound per square feet. Okay, so the value should be 100. Okay, this one also 100. So we need to choose between 24 hours or 12 hours. So in our case, we use 12 hours operation constant. So now we need to choose between internal shade or external shade. So based on the question just now, it means it states that there is no shades, or it means it is bare glass. So the value here should be 0.28 for east and also 0.51 for west. Okay, so we'll fill up here 0.28, 0.51. The last one is table 6. Table 6. Okay, the overall shade factor. The overall shade factor is based on the inside or outside blind. Alright, so in our case, it already mentioned that we use a medium color. Right, so okay, no shade with internal blind. We use internal blind with medium color. So we need to justify here 0.65 as our overall shade factor, because this is the inside Venetian blind with medium color. So I write here 0.65 for both sides. Alright, so we'll get the total value of 3115 and also 7197. So that's will produce around 22005 BTU per hour on the solar heat gain. Now we move to transmission heat gain. Okay, for transmission heat gain, we need to total up all of the area for glass, okay, including north and also south direction. So this one, the total area is 432.5 square feet. Okay, so I write here 432.5 square feet multiply with table 9. So we move to table 9. Alright, here we have external internal roof, but only one item for glass. Okay, so our glass is installed vertically. Okay, if your glass is installed horizontally, you should use this value. So for vertical glass, the value should be 1.13. Okay, 1.13. And the temperature difference is based on our first psychrometric analysis here, 17. Okay, this is the temperature difference. It produces 8308 BTU per hour. Okay, now for wall transmission heat gain, because we already calculated for east and also west direction for solar heat gain. For the transmission heat gain, we need to consider on the different side, which is north and also south. Okay, so for the north wall direction, we already calculated it is 450 square feet, and then for south direction is 650 square feet, and then we multiply with table 9. Okay, now we check again table 9. This is also external wall. Okay, external wall, so the value should be 0.48 also, because this is the brick wall with cement plaster on both sides. Okay, so remember, the external wall is exposed, can be exposed to the directly exposed to the sun, while for the internal wall is inside the building, never exposed to the sun. Okay, now I put here 0.48. And then the temperature difference also same 17, but with minus 5 here, it becomes 12. This one also 12. So it produces 2592 and then 3744. Okay, and then there is no partition we use. And then for the ceiling and also floor, so the area for ceiling is based on the our area here. Okay, floor area same 4225. Same with floor 4 to 5. So this one no need. Okay, and then multiply with table 9. Okay, so from table 9 we need to choose value for ceiling and also floor. Okay, so this is ceiling and floor, right? Okay, for ceiling we use here 0.22, 0.22, and for the floor, if our house is made by concrete floor, okay, or it means that you have more than one story, so we need to use 0.25. But if your house only have one floor, so it means that you need to use roof. Okay, so for our cases, we only have one floor and there is no concrete floor used here. So we use corrugated asbestos sheet with suspended board ceiling based on the question. Okay, here roof, that's why we use roof. So we need to use roof instead of concrete floor. Okay, so the value should be 0.28 and also 0.22 for the ceiling. Okay, now for ceiling I write 0.22, and then for the floor we replace with roof. Okay, remember, if you have more than one floor, you need to use concrete floor, which is 0.25. Now we multiply with the temperature difference. Okay, so same here, 17, but normally for ceiling and floor I minus 2. Okay, because there is a temperature drop. Okay, if the heat is transferred through ceiling and also floor, so it becomes 15 and also 15. So now we calculated again. Okay, becomes 1 3 9 4 3. Another one is 1 7 7 4 5. Okay, so it produce a total of 4 6 3 3 2 BTU per hour. Right, so that is your transmission heat gain. Now we move for the internal heat. Okay, so for the internal heat, we need to consider people, light, and also equipment. People, how many people we use? 50. So this one is empty. Multiply with table 10. So let's check table 10. Alright, so we use degree of activity for office worker here. The value in Malaysia is divided into sensible and also latent. So in our case, we currently fill up the sensible table. Okay, so for the sensible table, we take value of 245 for office worker. Okay, for latent heat we use 205. Okay, here I will write 245. It will produce 12250. Okay, 12250. Alright, so for the next item is light. So we use the same area as ceiling and also floor, which is 4225 area, and then you need to multiply with table 1. Okay, so table 1 basically give you the value of watt per square feet. Okay, so for office building the value should be 4, right? However, we also need to consider the value given in the question. So here lighting is already stated 4 watt per square feet, means that we need to use this value. So coincidentally it is same with the value from the table. If you have this case, you need to prefer to use the value from the question. Okay, no need to use table if the value from the question already stated. So we use 4 watt per square feet. Okay, here multiply with 4 watt per square feet, multiply with the type factor. So type factor is different between normal bulb and also fluorescent type. Right, for lamp, for light, sorry, the heat gain is calculated based on the total light watts multiplied with 3.4 for incandescent, or total light watts times 1.25 times 3.5. So the factor here is 1.25 for fluorescent type. Okay, the type factor 1.25. So this is your total watt, 4225 multiplied with 4, and then we need to type multiply with type factor 1.25 and then multiply with 3.4. We get the value of we got 71825 BTU per hour. And then for the equipment, so from the question it mentioned we have 40 equipment, right? Okay, 40 equipment, okay, rated at 350 watt. So we have 40, okay, this one is empty, multiply with type factor, which is the rate 350 watt, okay, then multiply with 3.4. Okay, so this basically is your conversion unit from watt into BTU per hour. So this produce 47600. So all of this we sum it to be 131,675. 131,675. Okay, let's calculate. And then for the room sensible heat subtotal, we need to add this, and also this. Okay, 3 item. Okay, plus it becomes through 200,012. Okay, so the safety factor is 10% from the previous value. 200,000, 10% is about 200, 20,000. Okay, 20,001. Okay, and then we add both, becomes 2, 2, 0, 0, 1, 2. Okay, so it's quite huge. Okay, the room sensible heat. Now we move to the outside air. Okay, outside air, the CFM is 7. Sorry, we need to use the value from this one. Okay, the highest one 750 from ventilation. So we put here 750. 750 multiply with bypass factor. So this one is from table 12. Okay, table 12. Sorry. Right. So for example is our office. Okay, it's not residence. It's not a small retail shop or factory. It's not a factory. It's not hospital. So if there is no related example based on our problem, we can use the second one, because this is the typical comfort application for many applications such as general, such as our office. Okay, so we take the value from 0.2 to 0.3. So the coil bypass factor basically is the amount of air that is passed to the coil. Okay. Okay. Sorry for we use the third one. The third one is the typical comfort application. This one is suitable for small load. Okay. So generally, if you did not know which type of application you want to use, you can use the third one. Okay. So the value is range between 0.1 to 0.2. Okay. So which value we want to use? The 0.1, 0.11, 0.12, or you want to use 0.20. Okay, so in our case, we will use the maximum value because it means we will play safe with our design. So bypass factor basically is this is our coil and this is your air pass through. So it means that 20%, if we take a bypass of 0.2, it means that 20% of the air is blocked by the coil. So only 80% is passed through the coil. So if you take 10%, it means that you assume that 90% is of the air is passed to the coil. So it will affect your cooling load factor. Right, so now I will take 0.2 value, okay, bypass factor, and this is your temperature difference, 17. So the value is 2779 BTU per hour. So we add with this one to 20012, it becomes 22279 1 BTU per hour. So this is your total effective room sensible heat, ERSH. So the next section is we were going to calculate the room latent heat. Okay, for the room latent heat, same here. We have 50 people. Okay, and then we'll multiply with table 10 that we have previously used. Okay, but just now we used for sensible heat 245. Now we use for latent heat 205. Okay, so I put here 205. Then we get 10250 BTU per hour. So because we already calculate the equipment, no need to recalculate it again. Okay, so this one is become empty. Then we put the safety factor 1025. Okay, 10% from the previous value. And then we calculate also the room latent heat to be 10250 plus 1025 becomes 11275 BTU per hour. Okay, and then for the outside air, the CFM we used just now is 750, and the specific humidity difference is set to be 64. Okay, you can recheck again the psychrometric analysis. Okay, we use the difference. And our bypass factor is fixed to be 0.2 as we write just now, 0.2. Okay, and then we multiply all of this value, it becomes 6528, and then you add with the previous value, you get 17,000 803. And then the next row is 1 plus 2. 1 is 222791, and the number 2 is 17803. It becomes 240594. Okay, and we reach the last part, which is outside and heat. So this is our CFM 750. Same 750. This is your temperature difference. Okay, 17. And for the specific humidity difference is 64. And then this is your bypass factor 0.2. This is we have multiply 0.2, and then you calculated 118 and also 26112. Okay, total up to be 37230. And then we add with the previous value, we got the grand total heat to be 277824 BTU per hour. So this value 277824 BTU per hour is our cooling load estimation value for our building. This value is very important in order to design the air distribution system on the next chapter. Alright, thank you.